So this is the original definitions given by Martin Casado. So where he said that, so I will use this hardware only for forwarding. I will take the brain or intelligence out of that hardware and I will put it at central location. So even with bigger topologies, all these devices would be acting as if only the forwarding plane functionalities would do only the forwarding functionalities. But actual centralized control or the control would be taken care by one centralized controller. So that is one definition or one approach. Because this is not a definition here. Everything is like how we gonna achieve the simplification or how we gonna achieve what your application demands. There might be different approaches we will see in the later slides. So the first thing is I can decouple control and data planes. That is one way. Other way of with SDN is like I have to enable a technology where I can have my network functionalities virtualized. Network function virtualization, NFV. So I can virtualize all the networking functionalities like routing, switching, firewalls, or load balancers. So I can virtualize all these things on a software running on physical hardware. I don't depend on my physical hardware because I know the functionality of each function. Something like if I take a load balancer, I know what it has to do. I will visualize it. But underlying, I should know someone has to facilitate this. That facilitator is called SDN. And the third concept is the leveraging the programming interfaces, also called APIs, to enable the communication between these devices and the controller. So based on the APIs, what APIs I have, I can provision my device, I can control my device, I can operate my whole fabric or the whole set of devices, whole topology. So these three technologies or three approaches, something like the first one is segmenting or decoupling control on the data planes, or having the underlying infrastructure to enable network function virtualizations on top of my physical infra. There are a few concepts to achieve this is like using the concepts of overlays. The third one is like leveraging programming interfaces, APIs. So these are the three approaches. Few of the models would use any one of them, or few would use all these approaches. So the objective is like based on the requirements, you can leverage all these functionalities to achieve what we want. What we want is like my whole network should be intelligent enough to understand what kind of packet it is coming, what policy I have. According to that, it has to forward the packet in an agile and resilient manner in secured environment. So let's see what is OpenFlow. So this is OpenFlow is something like a protocol for forwarding plane protocol, L2 protocol, where SDN controller can talk to the physical hardware. It can pass the information, what action it has to take. This is an open standard protocol developed by this Stanford University with the mission of a clean state. So this is a protocol where the controller can talk to these physical hardwares. So like this, we have other protocols also, but this is OpenFlow is this basic and very important on just first protocol. So moving on to the next, OpenDaylight. So OpenDaylight is something like I said, right? We are abstracting this control plane or decoupling the control plane from all the boxes and putting it one centralized location. That we call it a controller. So to develop that controller, it's an open source project funded by this all these platinum, gold, and silver, this premium or this prominent networking vendors or manufacturers. So they funded this project to develop this controller, centralized controller. This is focused on this is using OpenFlow as a protocol for this controller, OpenDaylight controller, to talk to all the boxes white box models, we can use this OpenDaylight controller. In this, the boxes should understand what is OpenFlow. Only then it can understand what controller is telling it to do. So we quickly see what are the networking or SDN models we have, programming network programming models or SDN models we have today. So as of now, that's traditional networking, right? How we are going configuration, we are configuring. So we are using the CLIs to put my configurations, or we have some management protocol called SNMP, simple network management protocol, where I can configure and also seek the information from the device for monitoring. And we have for monitoring, we have some other protocols called NetFlow. So in this case, the box itself is having both data plane and control plane. From these analytics tools or management tools, we are sending or we are using these three protocols to get information. And this is per box by box. I have to probe each box to get the information what I require. And moving on later, vendors like Cisco has come up with APIs. These are like programming interfaces. So we APIs is something like a request and response kind. I request for something, I will get something out of it. You can see the example is something like online calculator, where I have something like giving my arguments input 2 plus 2. What is 2 plus 2? If I give that as an input, I'm getting 4 as my output, right? So where I'm calling that APIs. So the third one is classical and pure form of SDN, where the controller is abstracted or decoupled from this physical hardware, and they communicate. The controller communicates to this box using these protocols like OpenFlow, Path Computation Ethernet Protocol (PCEP), or ITORS, Interface to Routing System. So netconf. So these are such different protocols. Now in this case, this is a classic definition where I am abstracting or decoupling this controller from the data plane. The next one is hybrid SDN. So there are few drawbacks when I take the controller out of the hardware, because for every flow I have to send what action it has to take. So instead of that, I can still put controller on the box. I can control the control plane of the device. So that is where this approach has come. Hybrid SDN. The fourth one is like network abstraction. I will build logical networks on top of the physical hardware. Sorry, on the top of physical underlay network. So where I can support multi-vendor on the single fabric or on the single set of devices or on my topology. So it uses a concept called overlays, or I can have something called virtual switch. Earlier we saw, right, something called API, application programming interface, where one controller is controlling the data planes of the devices. So this is information about an API. API is something like request and response model. I will ask for something, it will give me some response. So it is used to connect two pieces of software together. So I'm requesting for some information. So that device has to open a few APIs or a few set of URLs. So when I pass the required arguments, I'm getting my appropriate response as per my request. So model-driven programmability stack. So this is very important. I'm not going in depth right in this time. So in this, if you take devices, Cisco router or Cisco switches, let's take that show IP route or show IP interface brief. If you give any show commands, so the response we are getting, it is giving some response, right? So that is mostly human readable. But when I pass that information and put it into the system or into the programmable way, my laptop or my PC compute system doesn't understand, because the output was given to be human readable, more of human readable. That was old days where we are going to each of the boxes and doing the configurations and stuff. But these days, everything is controlled by the software, piece of software. Something like my one computer is controlling the other computers, like the controller is controlling the other white boxes. So in this case, it has to understand by the system. It shouldn't be understandable by the human. It should be understandable by the system. So when I give show IP route, what are the information it is giving, that should be easily readable by the system. Something like it can use some encoding methods like data formatting methods like JSON file or XML file. It should be in organized manner. Likewise, before something like, if I take one protocol called OSPF, it's the routing protocol. It might be having a hierarchy, right? That objects, different objects, or different within the class, it might be having some objects. All should be in certain order, organized in order, hierarchical manner. So some vendors like a Cisco, it is having its own hierarchy. If I take some vendors like Juniper, it is having its own hierarchy. So what modeling does is, so what Cisco understands and what Juniper understands, I want to model into the common state. I want to put in some common database or common format. That is what is called data modeling. So some of the examples are like ANG. If I achieve that, on top of that, I can use these methods like JSON and XML for encoding, and the protocols like netconf or restconf to get whatever information I request. And everything is based on API. So earlier I mentioned overlays. So what exactly is overlay is? So if you see in this bottom diagram, we have a physical devices connected. The topology, each of the devices are connected by some links, and we have enabled routing or reachability. So on top of this, we can build logical networks. On top of the same things, we can build my logical network. Logical network, if you see the logical network, right, the first one, it looks like it is directly connected to other two devices, although in between you have a router. So that is how it is it is completely abstracted from the underlay. For me, it looks like one topology. If I want to use the same physical topology for the different vendor, it might have its own different logical topology. So how we are achieving this concept is, we have some protocols like VXLAN, Lisp, GREs. So these are the few tunneling topologies. VXLAN for extending other cases, right? Segmentation information, all these things can be carry forwarded. So I strongly suggest you to learn the concept of VXLAN. If you want to learn more about SDN, start from you should know what is VXLAN, what is MPBGP, what is Lisp. So that VXLAN is a one such technology where we can build logical topology on top of physical infra. So now most of the times you see Fabric in SDN domains. Most of the vendors like Cisco or Juniper or New Age Networks, they keep on saying Fabric, Fabric, Fabric. So what is a Fabric? It's an overlay. So we have a physical infra. On top of that, we have a logical topology, right? That whole logical topology is a Fabric for me. So because I'm not controlling box by box in this case. So whenever I apply any policy, whenever I say that this set of endpoints has to talk to this set of endpoints, that is a policy for me. That is a set of rules. So based on the rules, I have my own overlay network, one topology. So I can like completely abstract the network out of the physical infrastructure. That is what is called fabrics. So these are few overlay protocols: MPLS, GREs, IPsec. In wireless, we have protocol called CAP, Lisp, OTV, DFA, and ACI is data center technology from Cisco. It also uses this overlay concept of overlay SDN. So just summing up, summarizing all the SDN things we have discussed. So in this topology, this is the complete architecture of SDN. So we have a networking devices, physical devices. These are the white boxes, which are which can understand OpenFlow in this case, or it might be any other protocol, PSEP or I2RS or netconf. So they are understanding some protocol. Using that protocol, if you take this example, this slide as an example, it says that OpenFlow. So all the devices should understand this OpenFlow, and I am controlling this from centralized controller. The second layer is called control layer. On control layer, it it can pass this information, or what flows it has to do, what policies it has to apply, can it allow this packet to reach this destination. So all this information or this logic is held by this controller. So here the network devices are dummy devices which has a forwarding plane or something like a muzzle, which can push the packet out of its exit interface or uh, some path based on that action information it received from the controller. So these things are called southbound APIs. This OpenFlow, because this is at the south side where the controller in this whole architecture, this is at the south side where the controller is sending some information to devices using some protocols. So those protocols or these calls or APIs are called southbound APIs. So now where we are defining my network logic. So that is where we have application layer. Based on the application, this controller is controlling this whole boxes, all these boxes. So likewise, at the start of this discussion, I said that we're just downloading an application from the internet or somewhere without bothering what is my hardware, physical hardware. Does does it do I have any Dell PC or Lenovo PC? I don't share that information. I just download the application based on the controller or based on the operating system, and then directly install on my PC. It can directly talk to the physical hardware via this operating system. The same analogy apply here. So I have one business logic. Let's say that I have a load balancing logic, networking load balancing. So that logic I just downloaded based on what controller I have. That application I have downloaded based on what controller I have. Then when I say that, when I put my information or when I give my use cases on that application gonna talk to controller using some APIs. Those are called northbound APIs. Then the controller will dictate the network devices what action it has to take using the southbound APIs. In this example, OpenFlow. So this is the whole architecture of SDN. The implementation might be different, but the high level logic is the same. Application will dictate what it wants, and it will ask the controller, you do this action for me. Then the controller will give some action items or action tasks to these networking devices, and then they forward the packet out of that exit interfaces. And the whole policies, enforcement, everything is controlled by the controller here. So these are the different protocols, SDN protocols in the networking, and at different levels. So on the device we have operating system, and the olden days we have something called SNMP for managing, or the CLIs. So they directly talk to the operating system, get some information. And we have some protocols called OpenFlow we discussed now, ONF protocol, Open Network Foundation protocol, where a controller would talk to this device. So likewise as OpenFlow, we have another industry protocol called OpenFlex. Initially it was with Cisco, now it is made as open source. So we have like IR2S, PCEP, BGPLS, and for OpenStack, we have Neutron. We have some agent called Neutron. And for orchestrators like Puppet, Chef, Ansible, and very important protocol is the netconf. This is becoming famous these days. Netconf on the REST conf. It is similar to the REST API, but to manage this networking configuration models. And we conclude this with SDN use cases, what we see here. So these are the high level network use cases, SDN use cases. The first one is the network abstraction. Using concept of overlays on the single physical infra, I can have my hundreds of overlay networks. What I can get out of it is the single physical infra. This is very much required for the cloud deployments where they are having the single infra, the same infra. On top of that, they are having like hosting applications for different vendors, thousands of vendors in a complete isolated and segmented manner. So multi-vendor support you can get using this concept called network abstraction. The second one is service deployments. So service deployments is like I want to deploy a load balancer. So I can just go and write an application now. I don't want to purchase a physical hardware these days with SDN because the physical infra is the same, and I have a controller which can dictate what my infra could do, or it is supposed to do now. So accordingly, I will write an application for one service, in this example, load balancer. And the load balancer will talk to the controller and it will give its metadata information, or it requests the controller to do such certain tasks. Then the controller would dictate all the networking devices to complete that task. And it will see whether the forwarding is happening as intended or not. So likewise, the third one is the traffic engineering. So it's very much useful for the service providers. Let's take an example like I have one customer or something like I am the one enterprise. So where hundreds of employees are leveraging the network, accessing the network. Few would use very critical, important business information. And let's take that few members are browsing that YouTube, and everything has to take one WAN link. It has to go outside of my campus. So certain data is very critical because there is business information, critical information, and certain set of traffic is YouTube traffic. That is, for me, it's not that much important. And WAN link, I'm using, I lease some MPLS link from service provider, which is very expensive. I have to pay huge amount when I use that link to send out my traffic. So when I keep on sending the YouTube traffic to the similar expensive link, it is adding more cost to me, right? I want to filter it out. I want to say that if it is YouTube, send it from the cheap ISP link or service provider link. For the critical information, take this low latency link, exit. So this kind of traffic engineering, right? Based on the traffic, I am redirecting to take with what is best suits me. So with SDN, we can do is very simple. And the other one is network function virtualization, NFVs. So similarly, like I want to do some routing functionalities. I want to write OSPF, what it does, OSPF is as the routing rate. The same thing, I want to write an application. I want to write a piece of software, or I want to have something called a firewall functionality. It has to block some malicious traffic, or something like I want to stop someone reaching these bad websites or malicious websites. I can write an application based on that IPS. So I can write all these things in a software. I don't need to purchase, go to vendors and get some hardware to do such functionalities. Everything I can virtualize it. And coming to the application areas, these are the different applications we have at different locations: data center, WAN, and branch campuses. So migrations, virtualization, analytics, QoS, traffic engineering. So now moving on to the job roles. So now everything is evolving as network is evolving. The job market is also evolving. So now it's not like someone who can connect Ethernet cables and go to log into each of the devices and do the configurations. Those are the olden days stories. Now, what industry is demanding, expecting from a engineer is he should able to translate the requirements into a networking phase. In our case, SDNs has to translate or has to program the network. Now it's not like configuring the network. He has to program the whole network based on the requirements. So for the requirements along with this networking concept, the industry experts you to be familiar with protocols like uh, uh, SDN protocols, and then few concepts like DevOps concepts like orchestrators, Ansible, Puppy, and Chef, which does automation based on the models. And you should be able to write some few uh, queries to get your output, few APIs, or to leverage the open up APIs, network programmability. It might be any programming language, either it might be Python or Perl or anything, but you should understand what is behind that, what is the intention you are doing that. You should understand what is REST call, what is what RESTful API is, how you can write an application by leveraging the APIs. So the kind of like the network engineering now translated to SDN engineer or the programmable engineer, and lot of scope is around this orchestration tools, DevOps, Ansible, Puppy, and Chef. So for all these things, this is the basic point. Understand the networking, understand software defined networking, and familiarize with the tools, what it demands, programmability, understanding of this overlay concept called VXLANs, Lisp, Python, uh, and how what actually happening behind these controllers. So this is now everything is evolving, like network is evolving. So the industry what demands from engineer is also has evolved now. Now network engineer is not a network admin now, is a programmer plus business guy plus network guy. So it's like a mix. You should understand the business logic first. You have to translate that, and you have to program your network to deliver the tasks for you. So this is the last slide we have. We will see these are the software market trends we see these days. So with SDN, right, in 2018, that is an $8 billion business. Now it is anticipated that by 2025 we see it at around 100 billions. So we see a rapid increase in the deployments, and also companies are looking at the advantages of it get, how what it delivers, the agile, that resiliency, the time to move to the business or deliver in output. It's all rapid now, and with the change of the cloud, all the cloud deployments are moving into the SDN to increase the scalability with resiliency, intellectually offload the traffic from or migrate the traffic from one location to other location. So vmotion, VM migration, as well as the workload migrations and traffic engineering. So now everything is rapid now. That is the reason most of the existing networking consumers like mostly the cloud consumers or the service providers or the enterprise. So everyone is adopting this SDN because they see the value out of it. And now we are almost into SDN because it's like a transition phase now, and we expect more to come in the coming years. And this number says that the change here from 2018 to 2025 is like a 10 times. We don't see with any other technologies doing this business. So I will